Thank you for joining me for this podcast on gas law practice. This is to learn how to do some of the general questions about gas laws preparatory to the test. So let's start right here. The first question, hydrogen peroxide. Get myself a pen here. There we go. Hydrogen peroxide in the presence of a catalyst decomposes into water and oxygen gas. Okay, so the formula for this, hydrogen peroxide, is a molecule which will decompose into water and oxygen gas. So this is a gas law problem dealing with this oxygen. First of all, it's a good idea to balance the equation. So if I'm given 34 grams of this, how many liters of this should I expect to form? Okay, so these answers should all be in liters, I can see. Well, we need to do a little stoichiometry here, so let's start out with the 34 grams. Let's see here, sorry about that. So the 34 grams of hydrogen peroxide, it turns out hydrogen peroxide is 34 grams per mole. So we're talking about 1 mole of hydrogen peroxide. We also know that it reacts on a 2-to-1 ratio. So 2 moles of hydrogen peroxide will make 1 mole of oxygen gas. And we know that at STP, 1 mole of oxygen gas should contain 22.4 liters. So the math here is fairly simple. It's 34 divided by 34 divided by 2 times 22.4. 22.4 divided by 2 is 11.2 liters. So the answer to the first one is C. The second one here, we have 1 mole of molecules, 6.02 times 10 to the 23rd. Here's a half a mole of molecules of water, and this is ammonia. So if you think about it, since we have 1 mole of ammonia gas and 1/2 a mole of water, if we were to divide this up into 2 halves, we would have a total of if we were to divide this up into 3 pieces here, 1/2 a mole of gas in each one of these pieces, then 1 mole would be 2/3 of this, and that would be the ammonia gas, and 1/2 a mole would be the water. So this lower third would be the water vapor. If the whole thing is 6 atmospheres total, then that would be divided up into 2 atmospheres, 2 atmospheres, and 2 atmospheres, for a total of 4 atmospheres of pressure would be the ammonia gas, and 2 atmospheres of pressure would be the water vapor. So apparently the answer is 4 atmospheres, or D should be the answer to how many, what's the partial pressure of the ammonia. Which gas deviates from ideality? Well, size matters. Helium is a little tiny atom, neon is bigger, krypton is even bigger, and radon is the biggest atom. The larger the size of the atom, the more it deviates from ideality, because the atoms themselves slosh around, the electrons leave more potential for there to be some attraction between these molecules. So the more attraction between the gas particles, the more they deviate from ideality. So the largest ones in this case would be radon. The answer is C. Which gas has a density of 3.74 grams per liter? Well, the way you figure this is 3.74 grams per 1 liter. If you think about it, it's 22.4 grams is 1 mole of a gas at STP. So if this is at STP, and even if it's not, we can calculate it, but liters cancel. This is liters per 1 mole. Liters cancel, so I end up having this many grams per mole, which is the molar mass. It turns out to be around 83 or 84, which, if you look on the periodic table, is the mass of krypton. So look on the periodic table, the square for krypton should have like 83 grams per mole under it. So the answer to this one would be D. Okay, number 5. Which gas has the highest average molecular speed? So the speed here has to do with its mass. The molecules with the lowest mass tend to have the highest amount of speed in order to have the same kinetic energy total. So if you've had a mixture of these gases together in one container, since they're all going to have the same kinetic energy, the ones with the smallest size here should have the highest average molecular speed. So the smallest gases would be the helium gas, of course, so the answer is A. Now here we have a question, the average kinetic energy of the gas molecules is, well, average kinetic energy is just this one piece right here, the temperature. So if I highlight that for you, just so you notice, the temperature is the whole thing. In fact, I see temperature listed here again for this next problem, but the average kinetic energy would be the temperature, and it's all the same in this case. The answer has to be E. If the pressure of each gas is increased at a constant temperature until the gas condenses, which gas will condense at the lowest pressure? Now, this is actually, it does not have to do with the temperature, so I'll go ahead and erase that if I can. Okay, there we go. What this has to do with is the amount of attraction between the particles. So methane being the lightest one here, methane is CH4, has the lowest mass. Ethane is got 2 carbons, propane has 3 carbons, and butane, as you know, has 4 carbons. So the larger the atomic mass here, it's getting larger as we go down, means that there's more attraction between the particles. So these particles have less attraction. As you go down, there's more attraction between the particles. So if you keep things constant, at a temperature constant like this, the gas will tend to condense at the lowest pressure if there's the greatest amount of attraction between the particles. So it looks to me like butane, since it has the highest molecular mass, which is the focus on this problem, it would condense at the lowest pressure. It takes less pressure for it to turn into a liquid. Okay, so number 8. The graph above shows the distribution of speed of molecules. Which graph shows the speed distribution at the lowest temperature? So what you see here is actually A is the gas at the lowest possible temperature, because average kinetic energy is the temperature. So since the gas here at this first part of the curve, A, has the lowest average kinetic energy or speed, it's actually reading the lowest temperature. The highest temperature would be like this. The molecules tend to flatten out. So curve A is the answer in this case. A flask has 1/2 a mole of helium, 1/2 a mole of neon, 1/2 a mole of argon. Total pressure is 600 millimeters. What is the partial pressure of helium in the flask? Okay, so you have a flask with 1/2 a mole, 1/2 a mole, and 1/2 a mole. Now, it turns out the particles themselves are what are causing the pressure. So according to the law of partial pressures, if there's 600 millimeters total in this, That would be 200 millimeters here, 200 millimeters here, and 200 millimeters here of pressure. So the partial pressure of the helium would just be this 1/3 of it, which would have to be the 200 millimeters. Pretty simple question. Propane gas, C3H burns at X. Okay, what is the correct coefficient when you balance this equation? All right, what that would be, since it's C3H8, when it burns an oxygen, it produces carbon dioxide and water. Okay, excellent. Well, we just have to go ahead and balance this equation. So, balancing this equation, we have 3 carbons, and over here we have 1 carbon, so I'm going to put a 3 here. That's a mandatory 3. 3 carbons. Now I have 8 hydrogens. Here's 2 hydrogens. I'm going to put a 4 here. It gives me a total of 6 oxygens here and 4 oxygens here for a total of 10 oxygens, meaning I need a 5 here. So the coefficient for oxygen would be 5, just like you see here in this case. The answer is C. So problem number 11. So we have 1 mole of helium, 1/4 mole neon, and 1/4 mole of argon. The total pressure in a rigid tank that contains this number of moles of gas is 6.0 atmospheres. So 6 atmospheres, if you were to divide this tank up into 6 chunks, one, two, three, 1, 2, 3, 4, 5, 6. I missed a little bit on that. So let's say we have 4 pieces here. That represents the helium. That would be like 1/4 of a mole there, 1/4 of a mole there, 1/4 of a mole there, 1/4 of a mole there. And then we have 1/4 of a mole is the total neon, and then 1/4 of a mole is the total argon. So out of this 6 atmospheres, 1, 2, 3, 1 mole is here. So divide this into 1 atmosphere for each of these. Since I'm dividing it by 6, that means that the helium is going to represent 4 of those atmospheres out of the 6. So see, the partial pressure of the helium is going to be 4/6 of the total. Okay, number 12. So the answer to 11 is D. Number 12, at what temperature and pressure would a gas be most likely to deviate from ideal? Well, gases tend to deviate from ideal when they're close together, in close proximity, because then the forces of attraction are greater. That tends to happen under high pressures. Also, it tends to happen under low temperatures, as the low temperatures allow the molecules to get closer together. So gases deviate from ideal behavior at low temperatures and high pressures. Of course, the opposite would be true at high temperatures and low pressures. That would be when they were most ideal. But of course, the answer to this is A. So here we have 1 mole of methane reacts with 1 mole of O2. So if we look at this, we see that 1 mole of this and 1 mole of that. I really need 2 moles of this oxygen to react fully with 1 mole of methane. So in fact, we're going to see a limiting reactant here with the methane. No, excuse me, the oxygen is going to be the limiting reactant here. Let me back up on that. If we need more oxygen, so the oxygen here is limiting, and we're only going to use half of the oxygen because we only have 1 mole of this. So that means we're only going to produce half as much product here or namely 1/2 of a mole of carbon dioxide and 1 mole of water vapor. So see, we needed more oxygen. They only supplied us with 1 mole. That means we're going to have 1 and 1/2 moles of total of the products. 1 mole of CO2, 1/2 a mole of CO2, and 1 mole of water. The answer is C. Number 14, the following gases has the greatest average molecular speed. Now that's related to the molar mass. So of these 6 molecules, which has the lowest molar mass? Well, if you go through and calculate them all, you'll find out that nitrogen has a molar mass of 14 times 2 for 28. That's the tiniest, lightest molecule of all 5 of these. So the answer must be C. The reason for that is, of course, 1/2 mv squared represents the particles. So if the mass here is the smallest, to have the same kinetic energy at a specific temperature, the velocity must be the greatest, which is the reason why this is happening. Number 15, which represents an ideal gas the most? Well, that would be under ideal gases like to be under high temperatures, and ideal gases like low pressures. Again, the reason I said before is that the further apart the molecules and the faster they're moving, the less attraction between the particles. And so here is high pressure, so that's the most ideal is going to be here under E, which is low pressure, and the temperature is not involved. So point E has the lowest pressure, and thus the largest volume, and so these particles are spread apart and will have more ideal behavior. Okay, here we need to solve for the ideal gas law. PV is equal to nRT. Let's see, so T is 300 degrees Celsius. R is given here as 0.08. And we want to solve for the number of moles first, and then later we find the molar mass. Pressure is 1.5 atmospheres, and the volume is 2.0 liters. So solving for N here, I get N is equal to 0.125 moles. So then, since I have 4 grams of it, and it's this many moles, I can do a final calculation. 4 grams divided by 0.125 moles gives me a molar mass of 32, which is probably the gas is oxygen. And the answer would have to be D, 32. The answer is D. For 15, the answer is E.